So, did you play?
Yeah.
Were you honest about it?
Yeah.
Now, being honest, your answer, raise your hand if it was pretty much the same as the Harvard graduates' answers. Yeah, I know. It's very rare that a student at your level knows the correct answer to that question. I love it. I love when I get to teach you things that you didn't know that you didn't know. Right? You thought you knew that, but you didn't. It's cool, right? It's cool to learn things that you don't know. The problem is with that one and with what we call common scientific misconceptions is that whole movie that you saw a piece of from like the 70s is about the fact that when you learn something wrong like that, it's with you forever. You can get to where you know the right answer, but you always sort of have to go around the wrong answer. It's kind of creepy. Anyway, where does the mass come from? Carbon dioxide from? Carbon dioxide from the air. That's the freaky part, is it's a gas, and somehow they're making wood out of it. Trees are solar-powered machines that turn air into wood. Oh my gosh.
Is wood just carbon?
Yeah. I mean, you could pretty much say that about life, Quentin, right? Life is just condensed carbon, kind of.
So my house is just condensed carbon.
It depends on what it's made of. Yeah, absolutely. Tree parts. Yep. So, good. I'm glad you know that now. Let's see if you can hang on to it. And did you balance the equation correctly? Were you able to do that without me? I know you're rusty, but it's not hard. You know, you just kind of start with the one that looks the least scary. In that case, for me, it's carbon. You put the 6 there, and then you do hydrogen. You put the 6 there, and those two are balanced. And oxygen would be scary in this, except that you have it all by itself over here. You can do whatever you want, right? So we want, is it 18? And this is 6, and so that means we want 12, and so we just put a 6 there. So chlorophyll is the important part as far as actually harnessing the sun's energy. We'll get to that later. Where this happens is in a structure that all plant cells have that they didn't start out with. We learned in the endosymbiotic theory. What part is that? Called the chloroplast. Good. Looks like that, more or less. You don't have to draw that. But basically, we've got a double membrane on the outside, and then we have all these stacks of membranes on the inside. When photosynthesis happens, it happens in 2 kind of separate sets of reactions. They're happening concurrently a lot of the time. That means at the same time, but not always. Turns out that only one of those sets of reactions requires light. The other one can just happen whenever. So we call them the light-dependent reactions and the light-independent reactions. We still sometimes use the old school name for the light-independent reactions, which is the Calvin cycle. So you should know that. That's named after the guy that discovered it, Melvin Calvin. We purposely don't use the old pair of terms we used to use for these. They used to be called the light reactions and the dark reactions, but that's misleading because the dark reactions don't just happen in the dark, they happen all the time. So we switched to light dependent and light independent. So we will be exploring those 2 separately, light dependent and light independent, tomorrow. This is a challenging chapter, maybe even more so than the last one. By the way, I forgot to change, but that's your latest test results. Nicely done. I did actually decide to put them on second quarter, just because I thought they were going to be lower, and I thought it'd be better to have them, not hurt you too much. But that's a nice way to start second quarter. So they're on second quarter. So yeah, you're about to start getting hit by terms that are brand new to you and processes that take some thinking. So please keep up. Know that it is definitely quiz season, and we'll be fine. This is one of those chapters that usually kids kind of freak out about, and they freak out about it enough that they do okay. So in order to know about these sets of reactions, you got to know where they happen. The chloroplast has a double membrane, just like the mitochondria, except minus the wrinkles on the inner membrane. But then it's got those stacks. And they almost look like a roll of quarters, right? And these little coin-shaped membranes that make up the stacks are called thylakoids. So there's a new one. And thylakoids come in stacks. We have a name for the stack as well. The stack is called a granum. This is where the chlorophyll is. And so which set of reactions happens here, do you think? Light dependent or light independent? This is where the light dependent reactions happen. Because that's where the chlorophyll is. That's the stuff that gets excited by sunlight. Now, if you remember the endosymbiotic theory, which says that the chloroplast is one of those two organelles that began as a free-living bacterium, if you think of it as a little bacterium, then the bacterium's cytoplasm or cytosol, the stuff that everything's floating in the chloroplast, that stuff is called the stroma. There's another term. And the stroma is where the light-independent reactions happen. So this process that we're starting to go through is the answer to the question, where does glucose come from, right? This is how a plant makes glucose using carbon dioxide from the air and the sun's energy harnessed by chlorophyll. We need to answer a different question, though, before we move on. There's a couple of high energy molecules involved in this. And one of them you really need to know before we go any further. Because glucose is great, but it's not spendable in the cell. It's not the thing that you can use to get a job done in the cell. You can't power anything directly with glucose. You have to convert glucose's chemical energy into a more accessible, more usable energy molecule. So who knows what that molecule is? ATP. Good. ATP is the name of the molecule. Which stands for adenosine triphosphate. You don't have to write chapter 8 again. I usually do this in a different order. But I wanted you to have a fun game to play while I was gone. Adenosine triphosphate describes the structure of the molecule, which has 3 components. Well, 5 if you count each phosphate separately. It is made of an adenine, a ribose, and 3 phosphates, which are shaped like this. So go ahead and draw those. And when you put them together the right way, and don't draw this one, we're going to draw it on the next slide, but this is what it looks like. Ben, what's your least favorite class?
Spanish, because I don't understand a word you understand.
It's like they have a different word for everything, isn't it?
Yeah, well, I don't like just sitting for an hour and just hearing what I don't understand.
The thing about ATP is the kind of the business end of ATP, what makes everything happen, is that 3rd phosphate right there. The phosphate on the end, sticking out, is very much like been in Spanish class. It does not want to be there at all. And given the slightest opportunity, it will pop right off of there. And in fact, when it does, the breaking of that bond releases a little bit of energy. In fact, just the right amount of energy, that your cell is basically designed around getting that little bit of energy from ATP and making things happen. So disconnecting the third phosphate, letting it pop off of there like it wants to, changes the name of the molecule. It's not ATP anymore, triphosphate. Now it's ADP, diphosphate. The phosphate it had still exists, and you get a little bit of energy that is very harnessable, if that's a word, by the cell. So that reaction, ATP becoming ADP, is kind of the big energy releasing reaction used to do work in the cell. You see something happen that requires energy, it's ATP that energy is coming from. We've seen this before, whether you remember or not. For a sticker, where have we seen ATP powering something before? Quite recently. The sodium-potassium pump, remember? What they don't show you in this little animation is they don't show you the rest of the ATP molecule, right? But that's the third phosphate. And what happens is ATP comes along, and it's basically the sodium-potassium pump is built so that when ATP comes along, ATP can stick that phosphate onto that pump, and it'll power it for one round. And then the phosphate pops off, and you need another ATP. You need a new ATP molecule every time that pump goes one round. And that's usually what it looks like. When ATP powers something, it does so by sticking a phosphate onto that something, sticking its third phosphate, which is so happy to get off of that ATP molecule that a little bit of energy gets released, and that cell part is built to harness that energy. Like, what's enough for you? When you grow up, get a nice job, which money do you want to have?
Like income-wise?
Like, how much is enough so that like you're not worried anymore? You've got all the money you need.
I don't know.
Is it a lot?
We haven't gotten to that part in personal finance yet.
Would you like to have a lot of money, Quentin?
Probably.
Are we talking like in the millions, maybe? She's nodding for you.
Okay.
So she says yes. Do you think he's going to keep all of that millions of dollars in cash at home?
Yes.
She recommends that you do not. Why is that? Why shouldn't he keep $1 million in cash at home?
Because somebody might come and take it.
Somebody could come and take it. Absolutely. What else? What other problems are there with keeping huge amounts of cash at home?
One, you don't have a protection policy. Let's say you put it in a bank. One, you can gain money as well. But
Okay.
if you keep it sitting at home.
Good.
Yeah.
But what do you mean by protection policy? Like she said, somebody could take it. Are there other things that could happen to it?
Well, like, let's say your house burned.
Oh, your house burns down. Yeah, it's true. You don't have that money anymore, do you? Or a flood would be a problem, maybe. Anything else? So gold is a better way to keep it. It's more stable as a
won't be able to carry
it doesn't rot and it's heavy and yeah. So we could say that cash is kind of an unstable way to keep large amounts of money.
What's gold?
Not really. You have a bunch of cash in your house, so we tempted to spend it.
Ooh, true. Yeah, out of sight, out of mind that's a good argument. So the analogy works pretty well for ATP. ATP is very much like the cash, the energy cache of the cell. Spendable, right? You can power anything with it. Think in terms of when people used to carry cash all the time. It's less and less now. But like cash, ATP is not super stable. You know, like every once in a while, Ben's just gonna leave Spanish class on a fake excuse. I go to the bathroom. Like ATP, every once in a while, will just deteriorate by itself. That third phosphate will just pop off of there. It's no good anymore, right? So instead of keeping all of your energy around as ATP, what you do is you use other molecules that are easy to convert into ATP. Glucose, in fact, has like 100 times almost the energy of ATP. And you got a whole system for converting it, for getting a lot of that ATP energy out of it. And that'll be chapter 9. Basically the reverse of photosynthesis. But it turns out ATP is involved both in photosynthesis and in its reverse, which is cell respiration. So you got to know about it ahead of time. That's not the only way you store energy, by the way. Sometimes you string a bunch of glucoses together in like a branching chain and store energy that way and send it to your liver for a sticker. What's that called? This is the hard one of the day. Nobody got it last period. What do you call a bunch of glucoses bonded together in a branching chain that you store in your liver that you can hack glucose molecules off and send them back to your bloodstream when you want? No, that's one of the hormones you use to keep that balance. Is that a hand? Not fat. Fat is an even bigger energy storage. Fat is when you know you have way too much and you got to pack it and you're not going to use it for a long time because fat's pretty expensive to break down. So yes, fat is absolutely, that's pound for pound the most energy you can store. This is more temporary. It's just a bunch of glucoses. There it is, glycogen. Remember? Animal starch as opposed to amylose, which is plant starch. Same purpose, store a bunch of glucose. Anyway, you keep just a small amount of ATP around, a wallet's worth of cash. And the rest you store in molecules like glucose, glycogen, and fat.
Yeah.
That's probably good for Monday. You're aware that it's quiz season. I think that's enough of an assignment that I don't feel like I need to give you further work.